I recall that the first time I met Igor Shpalinski was here in Winnie, when we both were attending a conference on algebraic geometry and coding theory. But I don't remember how long ago it was. So it is a great pleasure for me to return here this year, to attend a conference in his honor. So I wish him a happy 60th birthday and have many productive years to come. So today I will talk about connected, undirected graphs. So I would like to think of them as the objects corresponding to number fields. Okay. So in number theory, we consider algebraic extensions of number fields. So the corresponding objects in the graph side are the unramified covers. Okay. So the purpose of this talk is to explain the graph theoretic counterpart of some important results concerning the field extensions in number theory. Okay. So let me start by explaining what is an unramified cover. Okay. So if we have a graph X down here, and we have another graph Y up there. So we have alpha, which is a graph homomorphism, which takes the vertices to vertices and edges to edges. We want this alpha to be surjective. And we also want this alpha to be a local isomorphism. So that means that if I have a point upstairs and it has a bunch of neighbors like that, then you look at the projected image, that's exactly the same thing. Okay. So now, when we have number fields, we consider Galois extensions. So I want to do the same for the graphs. Okay. So if I have a cover alpha, okay. So what is an automorphism, a cover? Okay. So that is the automorphism of the graph such that the diagram commutes. Okay. So when you think about it, so if you take a vertex downstairs and you look at its fiber upstairs, so there's a bunch of points upstairs. So what this automorphism gamma can do is to permute the points on the fiber because it has to preserve this projection. Okay. So once I know that a point down here, say, is moved to a point, another point on the fiber, then its neighbor, will follow. And so then we know that how the neighbor points should go, and then we propagate because the graphs are connected. So once you know this, where this one point goes, then you know the rest. Okay. So a graph automorphism is determined by its action on one fiber. Okay, it can be any fiber because the graph X is connected. Okay. So we call this cover a normal cover if this automorphism group is large enough, namely it acts transitively on the fiber. Okay. So if you think about a case that if you take a point, you look at a fiber, if that fiber has finitely many points, okay, then the number of points will be the same regardless of which vertex downstairs you choose. And that common number is called the degree of the cover. And so if this cover alpha has a finite degree, and then it is a Galois, then if and only if the size of automorphism group is the same as the size of the fiber. That's exactly the same as what happened for number fields extension. If you have a finite extension, which is a Galois, if and only if the automorphism group has a size equal to the degree. Okay. So now if I think of this X corresponds to a number field, okay, and in number field we talk about algebraic closure. So for the graph, the role of algebraic closure is played by the universal cover. Okay, that's the highest cover, largest cover that we can take. And the universal cover being simply connected is a tree. Okay. So from the universal cover to the graph itself, there's a natural projection. And this projection is a normal cover. And the Galois group is naturally isomorphic to the fundamental group of the graph X. So the fundamental group plays the role of the absolute Galois group. Okay. And when we talk about fundamental group, we need to choose a base point. But again, since the graph is connected, it doesn't matter which base point we choose. All the groups are isomorphic. Okay. So the next thing is about subcover. Okay. So if I have a cover from Y to X, okay, and if I have one subcover called a beta from Y to Z, I have another subcover called a beta prime from Y to Z prime. Okay. So you think of that just when we have number field extension, you think of that as an abstract extension, and here we did not embed it do not have the field embedded in algebraic closure. So likewise here we have two finite subcovers, just abstract cover. So I want to say that when they are equivalent, so they are equivalent if I can, first of all, what is a subcover? A subcover means that if I have a map, covering map from Y to Z, then I should be able to find another covering map called a gamma from Z to X such that the diagram commutes. Okay. So since this cover from Z to X, this gamma is uniquely determined by alpha and the beta, so I would just write this gamma as alpha over beta. Okay. So now if I have two subcovers, so on the beta prime side, I have a map alpha over beta prime. Okay. So I want to know that whether these two subcovers are equivalent. That means that I should be able to find an automorphism of the graph Z to Z prime, such that the top diagram commutes and the bottom diagram commutes. Okay. So so then we collect together all the subcovers which are equivalent to each other. So I have equivalence class of the subcovers. Okay. So in my mind is that if I think of this cover alpha corresponds, well, which is Y over X, which corresponds to field extension K over F. And then for the field extension, we have intermediate fields. Then for the graph cover, well, the intermediate fields will correspond to equivalence classes of subcovers. So we all learned that the fundamental theorem of, the Galois theory for the fields. Now we have the same thing about the Galois theory for the graph covers. Okay. So let me start with a cover which is Y over X, which is a normal, okay? And I have a Galois group. I denote the Galois group by G alpha. Okay. So then I consider the equivalence classes of subcovers. Okay. So if this Y over X is Galois, okay, then Y over Z certainly is also Galois, so it has a Galois group G beta. So if I take equivalence classes of the subcovers, then the corresponding the group G beta viewed as a subgroup of G alpha, they will be the same. So then to each equivalence class of subcover, we can map it to its Galois group G beta, and this sets up a one-to-one correspondence between the classes of subcovers and the subgroups of the Galois group. Okay. And also, when I look at the down part from z to x, well, if this quotient map from z to x is a normal cover if and only if this group G beta is a normal subgroup. And in that case, the Galois group of alpha over beta is the Galois group of G alpha over G beta. So that's exactly the same as what happened in number theory. Okay. And in the case of graphs, so when this thing happens, when this G beta is a normal subgroup, I'm just to call this beta a normal subcover for short. Okay. So, and the third thing I want to say is that, so if I start with the y over x, which is a normal cover, then the algebraic closure of y certainly is also algebraic, universal cover of y is also universal cover of x. So that allows us to embed the fundamental group of y as a subgroup of the fundamental group of x. Okay. And then since y over x is a normal cover, so this Galois group, G alpha, is isomorphic to the quotient of two fundamental groups. So in next slides, I want to say a little bit about the fundamental group of x. Okay. So let's start with x, which is a finite graph, say with m vertices and m edges. Okay. Then in this case, the fundamental group is a free group with rank equal to m minus m plus 1. Now, if you recall that a fundamental group, well, is each element is a homotopy class of the path starting and ending at x. So in a graph, we don't have much homotopy to talk about. So which just means that if you just take a loop starting and ending at x, you may go out wandering around, then you come back. So there's a lot of backtracking. So each element or each homotopy class is represented by a backtrackless walk, or starting and ending at x. Okay. So let me just briefly say that how we can find a generator for this fundamental group. Okay. So the easiest way is to start with a spanning tree. So spanning tree means that in this graph, you find a subtree which sits inside the graph. Okay. So you go as far as you can, and so on. Okay. So until you cannot add any more edges to it. So then this maximum tree, which sits inside your graph, should go through all the vertices. Okay. So as a tree, that means that the number of edges you use is the number of vertices minus 1. So you have used n minus 1 edges. Then you look at each unused edge. Say, suppose there's an unused edge here. So if you add this edge to this tree, then something is wrong. Otherwise, you would have this edge, included to begin with. So what's wrong is that you see a loop, you see a cycle. So each unused edge will create for you a cycle, a loop here. So if your base point x is somewhere here, then you will start from this x, then you go to this loop, then you follow this loop, then you come back to x. So each unused edge will correspond to, well, a unique element in the fundamental group. Okay. And this creates for you exactly the independent generators for the fundamental group. So also in this way, when we choose the generator for this fundamental group, we can control the length of this cycle we used. It's bounded by twice of the number of vertices minus 1. Okay. So if let me just look at some special cases. Say if I start with a graph which fundamental group has rank 0, which means that after you have done this maximum tree, you don't have any edges left over. That means you start with the tree itself. And the tree itself is its own universal cover. So there's no cover for this tree at all. So it's not an interesting graph to think about. Okay. And the next case is when the rank is 1. So that means that there's only one unused cycle, okay, say here. Okay, so when you look at this remaining part, they are not interesting. When you look at the cover, all that matters is that you find covers of this cycle first, then you just add this remaining part to it. These are the hanging objects, which does not contribute to anything about the cover. Okay, so for this reason, from now on, we are going to get rid of all this vertices, which has only, has the degree 1. So after we remove the very end, then we can keep on going. So I can remove all these hanging edges outside. So assume that each vertex has degree at least 2. And now in this case, so if my graph is a cycle, then for each degree, d, it has only one cover of degree d. So you just open up this cycle, you roll around it d times, then put it back. So in this case, the cover is also very clear. It's not interesting. So we will not consider this case. So we should only consider the case that the rank of the fundamental group is at least 2. Okay, and we remove this odds and ends, assume that each vertex has degree at least 2. Okay. So now let's talk about the various theorems in number theory that I would like to find their graph theoretic analogues. So the first is that how one describes the finite Galois extensions of a given number field. Okay. So if I start with a number field F, which is the base field, okay, and I take a finite extension K, okay, so one can consider the, this slide, the earlier part is written for the general audience. So in the field Q, we consider the integers, and in the number field, we consider the elements which are integral over Z, and they form a ring. And this ring usually is not a unique factorization domain, but if we look at the non-zero ideals in this ring, and then there's a unique factorization as a product of the maximal ideals, and it's unique up to order. So when we have a number field, these maximal ideals in the ring of integers play the role of primes. Okay, this is what I'm thinking about. Okay. So now, if I have this finite extension of number fields, downstairs I take a prime P, and then I multiply by the ring of integers upstairs. I make it a prime upstairs. Okay. And so it's an ideal in the ring of integers, so it factors as a product of the maximal ideals upstairs. Okay. So here the PIs here are the distinct primes upstairs. Okay. So when these exponents are all 1, we say that this prime P is unramified upstairs. And this is the case for almost all the primes downstairs. Okay. And when we look at this factorization, there's a special case, namely that our exponents are all 1, and also each primes, this P primes upstairs, have the same degree as the primes downstairs. Another way to say is that the number of distinct primes upstairs is equal to the degree of extension. Okay. So when this happens, we say that this prime P downstairs splits completely upstairs. Okay. So the primes downstairs with splitting completing upstairs are very important because they give you a way to describe, actually to determine Galois extensions. So this is one way to describe the finite Galois extensions of a given number field F. Namely, they are determined by the primes downstairs, which split completely upstairs. So this is called a reciprocity law. So I want to see whether this also holds for the graphs. Okay. So first I need to talk about what are the primes in a graph. Okay. So, so when we are given a graph, what we are interested in is a geodesic cycle. Okay. So that's a closed walk and with no backtrack. And well, to avoid the special kind of the walk which looks like this, if I starting from down here, I travel along the loop, then come back. So if I starting from the downstairs here, then there's no backtrack. But if I start from any other point, then there will be backtrack. So this is not a standard geodesic cycle you have in mind. The ones you have in mind are those without the tails. Okay. So to say that, that means that if I travel along it twice, there's no backtracking, then that is a geodesic cycle. Okay. And so if I look at the geodesic cycles, some of that, we call that a primitive. That is that it's not obtained by traveling along a shorter geodesic cycle more than once. Okay. So therefore, if we look at all the geodesic cycles, so they are either primitive or a power of primitive cycles. So only two kinds. Either, okay. And so for graph, the primes are the primitive geodesic cycles, but we are going to ignore the starting point, so we call that the equivalence class of the primitive geodesic cycles. Okay. So the assumption that the rank is at least 2 implies that this graph will have infinitely many primes. Okay. Okay. So now that we know what is a prime downstairs and also prime upstairs, now if I have a finite cover, okay, so if I take a prime upstairs, I project it down, then we know that it's also a geodesic cycle, so it is a prime power. Okay. So in the length is the length of the prime downstairs times k. So then the prime, capital P here project to the lower p, we call this capital P the prime upstairs, lying above the P downstairs. Okay. So we say that a prime P downstairs splits completely upstairs if all the primes upstairs have the same length as the prime downstairs. In other words, if you lift the prime downstairs up, then each lifting is closed. So here is the theorem about characterizing finite normal covers. Okay. So assume that the base graph is finite, okay, with n vertices, and I start with a finite normal cover. Okay. And so I look at its subcover. So I want to know that when two normal subcovers are equivalent. So this corresponds to in the case of number fields, k over f, I want to know that when two intermediate fields, which are normal over, which are Galois over downstairs, when they are the same. Okay. So the answer in number field case says that they have the same splitting, the same prime, which splitting completely in both fields. So it's similar for the case of graphs. Okay. You also look at the primes downstairs, which split completely in the first subcover and in the second subcover. Okay. Only that for the case of graphs, you do not need to consider all the primes because our graph is finite. You only need to consider the primes with a bounded length. And the bound for that length, is 4n times d, which is the maximum degree of the quotient cover, minus d minus 1. Okay. So in other words, that the number theoretic analog holds for the graphs, and also the criterion we need is stronger. We only need to consider finite many, the splitting of the finite many primes with that bounded length. Okay. And if I also want to consider subcovers which are not necessarily normal, then we can have a similar result. Now, in this case, instead of considering how the primes split, you consider the cycles downstairs of a bounded length. And when you lift them, they lift to a closed cycle upstairs. And you only have to check the cycles of length up to twice nd minus 1 in both. So if the two sets agree, and then the two subcovers are equivalent. So the next question I'm going to consider is the Chebotarev density theorem. Okay. So in number theory, Chebotarev density theorem is an extension of a Dirichlet's theorem. Okay. So Dirichlet's theorem says the following. Okay. If you give yourself a modulus and you consider the remainder mod m, so there are m of them, so they partition the integers into this R subsets. And so that among the integers, we have primes. We want to know that where the primes lie in which arithmetic progression. Okay. So if R and M are not co-prime, then in that arithmetic progression, you can only find many, at most one prime. So we ignore those. So we look at the remaining ones with residue, which is a co-prime to M, and they are phi M such arithmetic progressions. So then the primes, except for finite many of them, will fall in this phi M arithmetic progressions. And Dirichlet's theorem says that the primes are uniformly distributed among these arithmetic progressions, in the sense that in each arithmetic progression, the primes contained in there has natural density 1 over phi M. So then to describe the Chebotarev density theorem, now let me just give a general setup. Suppose I have a finite Galois extension, K over F, with a Galois group G. Okay. So then to each prime downstairs, we can associate a conjugacy class of G that is called a Frobenius conjugacy class. So the thing is that this is a finite Galois extension, so this Galois group is finite. This finite group has finitely many conjugacy classes. And the downstairs, there are infinitely many primes, which are unramified upstairs. To each prime, we have the Frobenius conjugacy class, and it is one of the conjugacy class of G. So we have infinitely many conjugacy classes called the Frobenius conjugacy class. We want to know how they are distributed among the finitely many conjugacy classes of G. So for that, so we give ourselves any conjugacy class C of G, and we just collect those primes such that the Frobenius class is equal to C. Okay. So we want to know that, well, how many primes will fall into this set. And the Chebotarev density theorem says that the Frobenius conjugacy classes are uniformly distributed. Okay. And that distribution is with respect to the natural density. So namely, we compare the number of primes in the set with the norm bounded by R versus the number of primes, all primes with norm bounded by R. So we look at this quotient and letting R go to infinity, and the limit exists. And the limit is very nice. It's the size of C over size of G. Okay. So in the case, if this field downstairs is a Q and upstairs is cyclotomic field, and then the Galois group is isomorphic to Z mod, the multiplicity group of Z mod MZ. So the size of Galois group is a phi M. And since this group is abelian, so each conjugacy class is a singleton, so this upstairs is 1. Okay. So then for each P not dividing M, that P is unramified in K. So the Frobenius P actually is nothing but just an integer P, which is viewed inside this Z mod MZ cross. So namely, so you look at each element in Z mod MZ cross is arithmetic progression represented by some element co-prime to M. So Frobenius P is equal, has that same residue, means that it falls in the same class. So this tells you that Chebotarev density theorem reduces to Dirichlet's theorem. Okay, now Let's go to the case of graphs. Okay. So let me start with normal, finite normal cover, y over x. Okay. So if downstairs I pick up a prime, so which is a closed geodesic like that, say it goes through a point, a vertex x. So on top of x there, well, we have finite many pre-images. So I pick up any point called a y. Okay. So I lift this loop upstairs. So then it should come back to a point which will project to x again. So the ending point, z, also lies in the same fiber. Okay. Now, since this is a Galois cover with a Galois group G, that means that there's a unique element in the Galois group which sends y to z. And that may call that element gamma y. Okay. So if I pick up another starting point, then I will have another ending point. I have another element, gamma y prime. Okay. So when you choose a different starting point, the gamma y and the gamma y prime differ by conjugation. So this tells you that the conjugacy class of gamma y is independent of choice of the starting point, and that is the Frobenius class associated to the prime p. Okay. So we do exactly the same thing as what we did for number fields. Okay. We give ourselves a conjugacy class of the Galois group. We collect all the primes downstairs with the Frobenius class equal to C. And so I asked how the primes are distributed there. Okay. So Tara showed that the Frobenius conjugacy classes are uniformly distributed, but with respect to the Dirichlet density. Okay. So let me explain a little bit of Dirichlet density. Okay. So to a graph x, we can define a so-called a zeta function. So it's a product over all the primes of x of 1 over 1 minus u to the length of prime. Okay. So this infinite product converges for absolute value of u, well, small. Okay. So, and turns out that the radius of convergence is 1 over lambda x. This lambda x is some number greater than 1. If the graph is a q plus 1 regular, then this lambda is equal to q. Okay. And also, 1 over lambda x itself is the first pole of this zeta function, which is the pole which is the closest to the origin, u equal to 0. Okay. So I have this zeta function. If I take a log of this zeta function, then the dominating term is precisely the summation of u to the length of prime for the prime p inside x. Okay. So the Dirichlet density is that you take the quotient, the numerator is the u to the length of prime for the prime in the given set, okay, and denominator is also all primes. Then you consider the limit as u goes to the approaches the first pole from the left-hand side. And that ratio is equal to the size of C over size of a Galois group. Okay. So then the natural question is to ask whether the Chebotarev density theorem holds for natural density. Okay. So this was actually considered by Hashimoto first, and he gave a proof. He published his proof, and later we found some problem in the argument. So we came up with this theorem, okay, which says that it's conditionally, that it holds conditionally. Okay. So the Chebotarev density theorem will hold for the natural density for one conjugacy class, okay, if and only if it holds for all the conjugacy classes, and if and only if there's some equality of the identity. So this equality is that you look at the primes, the length of the primes are downstairs, and the length of the primes, the GCD of the length of primes downstairs, and compare that to the GCD of length of primes upstairs. If the two GCDs agree, then the natural density holds. Otherwise, it doesn't. Okay. And the Stark and Terrace prove that when you compare the GCD of the lengths downstairs and upstairs, So the upstairs is either the same as the downstairs or it's twice of that downstairs. And both cases will occur. Okay. So when should I end?
We still have 5 minutes between questions. We start at 5 minutes.
I have 5 minutes, not including question, because I started late. Okay, so I just want to give you a very rough idea why it doesn't happen. Okay, so let's consider the situation. The downstairs is this graph X, 1 point with 2 loops. The upstairs is a twofold cover. Okay, you leave this point to 2 points. Okay. And clearly, the GCD of the length downstairs is equal to 1, and the fundamental group has rank 2. Okay. And for the upstairs, because to get a loop, it has to be even length, so the GCD of the length, the prime, is equal to 2. Okay. So for this twofold cover, Galois group has 2 elements. Let's call that a plus-minus identity. Okay. So this is abelian, so I have 2 conjugacy classes. So let's see what are the primes which will fall into the conjugacy class of identity. So by the way, we define the Frobenius. That means that when you take a prime downstairs, the Frobenius is trivial. That means that it should end at the same point. Okay. So for this cover, for that to happen, that means that see, if I start with a loop, which is say of length 1, when you lift it up, well, it's not going to be closed. So if the loop downstairs with odd length will have Frobenius, which is in the C minus, and the loops downstairs, which is even length, will have Frobenius, which is in the C plus. Okay. So I want to show to you that they do not have a natural density. So first of all, we know that a Dirichlet density is equal to 1/2. So if natural density holds, then it's equal to its Dirichlet density. It should also equal to 1/2. Let's see what happens if natural density holds. Okay. So let me just do that for the case of C plus. So I look at I consider the natural density. So I consider the number of primes falling in the first class, with the length that's bounded by the even length 2r, and over all the primes, the number of all the primes of length bounded by 2r. So this limit just should be 1/2, and I consider the same thing, but now the cutting length is odd, 2r plus 1. That subsequence also have the same limit, 1/2. Okay. But then as I described that for all the primes in this class C plus, the primes have even length. So therefore, the second set is the same as the first set. So this limit tells you that we have the primes of length bounded by even number 2r versus the number of primes bounded by the odd length 2r plus 1. As r goes to infinity, this ratio should equal to 1. Okay. Now, on the other hand, there's a prime number theorem, which tells you that how many primes there are with a length, which is r times the delta x, okay? And also the number of primes of length, which is smaller than r times delta x. So you see that all the primes of length smaller than r times delta x actually is a fraction of the number upstairs. It's smaller than the number upstairs. Okay. So if you use this formula to compare that quotient, you find out that the number you get is 1 over lambda to the delta x. Okay. So this delta x for our case is equal to 1. And the question is, what is lambda x? So as I said before, this 1 over lambda is the first pole of the zeta function. And another way to see this lambda x is that you look at the edge adjacency matrix, and it's the largest eigenvalue in absolute value. Okay. So in our particular case, the graph is very simple, only has 2 loops. So one is E1, and the other direction is bar, is the opposite orientation, the same with E2 and E2 bar. And the neighbor of, say, E1 will be all the other edges except going backwards. So you find out that the adjacency matrix for the directed edges look like this, you find out that the lambda is equal to 3. So the limit on the left-hand side is 1/3, on the right-hand side is 1, so that's a contradiction. Okay. And to prove the theorem itself, that one uses the allotted behavior of the Artin-L function attached to the graph. Since I don't have time, I'm going to skip that. Should I say the next one? I only have 2 slides. Let me. Okay. So the last question I want to consider is the isospectrality. So for the number fields, the question is that can you find 2 non-isomorphic number fields which have the same Dirichlet zeta function? In other words, that are such that I have 2 extensions of the number field F. You take a prime downstairs, and you look at the primes upstairs sitting over P in each field. So there should be a norm-preserving bijection from one set to the other. Okay. And for the number fields, there's a nice way, a nice algebraic way to decide this. That is that you embed these 2 fields into a common Galois extension, L, okay? And think of these 2 fields as the fixed field of 2 subgroups, H and H prime of the Galois group G, okay? So then the 2 fields are isospectral if and only if there's algebraic condition on these 2 groups, H and H prime. So the condition is that these 2 groups should be locally conjugate, okay? So that means that to each conjugate class in the big group G, you intersect it with the subgroup H and H prime, the cardinality should be the same. Okay. And so this criterion, which is already in the Cassels-Furlish, was extended by Sunada to compact Riemannian manifolds. So this is a very famous work of Sunada. Okay. So our question is that what happens for the graphs? Okay. So for the graphs, we cannot arbitrarily embed 2 extensions in another. So I start with the case that I have a finite normal extension, and I start with the 2 subcovers and ask whether they are equivalent or not. Okay. So this is work of Samodi, which says that the 2 Galois subgroups of the subcover, G beta and G beta prime, these are the H and H prime before. They are locally conjugate, which is the same condition as this condition A here. Okay. So that is equivalent to the case that each prime, P in X, downstairs, you look at the primes in the Z and the Z prime upstairs, and there should be a norm length-preserving bijection. So this part is very similar to what happens in number field case, okay? And the second condition here implies that the 2 graphs are isospectral, namely they have the adjacency of matrices have the same eigenvalues. But Samodi has a further simpler explanation is that you do not need to compare all the primes above P, but you only need to count the primes above P which have the same length as a P, okay? And in the joint work with Huang, that we further reduce the consideration. You don't need to consider all the primes P, but you only need to consider all the primes P of a bounded length. And so so that uses the things we said earlier that are for the generators of the fundamental group, and also to use the Galois correspondence and so on. But the proof is very nice, but I don't have time, so you can watch it on the recording. Thank you very much.
So maybe we have time for one quick question. No one's.
Can you extend this? Can you extend this machinery to include class groups, class numbers, and so on?
That was my original motivation, but I haven't gone there yet. Okay, so there's one thing is that the Galois group is a free group of a length Rx, and that you know, which is quite different from the Galois group for the number fields, which in the number field case is a lot more complicated. But you can consider the finite abelian extensions, etc., that is sort of very similar to the class field theory. But in this case, I do not know how interesting it is. Yeah.
And another completely different question is, there are many graph problems are known to be computationally difficult. Can you translate that to number theory problems?
This is the reverse direction. I haven't thought much about that, but that's a very good question. I hope somebody in the audience can give me some input.
Finding the Galois group of the number field is quite tricky once the degree goes up. But I'm not saying it's empty complete, but it's computationally impractical to go beyond degree 15 extensions or something.
Yes.
But we also have an algorithm which gives you a combinatorial way to find the Galois closure of a given finite extension. So for number fields, that if you're given a finite extension, so you view that as a simple extension, you write down the irreducible polynomial, so you have the roots, etc. You just join the roots to get a Galois closure. But for the graphs, you don't have that, but we have a way to find the normal closure of a given finite cover. Yeah.